1, permutations and combinations. Objective, to count permutations, to count combinations. Let's take a look at this example. We have 3 types of snowboards and 2 types of boots. How many choices does the store offer for snowboarding equipment? If we look at the next slide, we can say there are going to be 6 choices. All mountain and then soft, all mountain, hybrid, and so on. This is an example of the fundamental counting principle. Another way to count the choices in this example is to get the 3 choices and the 2 choices and multiply them together. If there's more than 2 choices, then you multiply all the choices together. Let's use the fundamental counting principle to figure out the number of different ways to frame a picture. We have 12 different styles, 55 different colors, and 11 types of shades of blue. So we take all of these choices and we multiply them together, and that's how many choices we'll have. Let's use the counting principle with and without repetition. So the standard configuration for a Texas license plate is 1 letter, followed by 2 digits, followed by 3 letters. So let's take a look at how many different license plates are possible if digits and letters can be repeated, and when they cannot be repeated. Okay, in the first example, everywhere there's a letter, there's 26 possibilities because they can be repeated. And for number of digits, there's 10. But watch what happens in B. After we choose a letter in the first slot, then there are only going to be 25 letters as an option for the second, 24 for the third, and 23 for the fourth. And the same thing happens for the numbers. Your turn. Use the counting principle to determine this answer. Go ahead and pause the video and find your answer. Here's your answer. Let's now take a look at permutations. We're going to use the fundamental counting principle to find the number of permutations for A, B, and C. These are choices for the first letter, followed by 2 choices for the second letter, finally only 1 choice for the last letter. What we're doing here, 3 times 2 times 1, is called a factorial, and we have a symbol. It's an exclamation point. We can call this 3 factorial. All right, let's take a look at 10 teams are competing in the final round of the Olympic 4-person bobsledding team. Okay, how many different ways can the bobsledding teams finish the competitions? Remember, there's 10 teams. And the B is, how many different ways can we get a first, second, and third gold, silver, and bronze medals? Okay, for part A, we're just doing what we did before in the counting principle, 10 times 9 times 8 times 7 times 6, and so on. That is a factorial. That is 10 factorial. Now for the B part, remember there's only 3 places for gold, silver, and bronze. So for the gold, there's 10 ways, and then for the silver, 9, and bronze, there's going to be 8. This is known as a permutation. Permutations are n objects taken R at a time. So for that previous example, there were 10 objects, and we were only going to take them 3 at a time because those are only the winners. And this is the formula for a permutation. And here's an example using numbers and then reducing. Okay, let's take a look at a science fair, and there are 10 contestants, very similar to the last problem. We have a first, second, and third place. This tells me right away that order is important. It is a permutation, and so it'll be what we call a permutation of 10 chosen 3 ways. And here's an example of how to use the formula and then how to simplify. Okay, your turn. Actually, it's my turn to do 4A, and so I'm going to do the first one. And remember, the formula is 5 factorial all over, and then you're going to subtract the 2 numbers, 4 times 3 factorial. And this is going to be 5 times 4 times 3 times 2 times 1. The bottom is 2 factorial, which is 2 times 1. We can reduce, and then we're going to have 20 times 3, which is 60. On the second one, this is 4 factorial all over 4 minus 1 factorial. This is 4 times 3 times 2 times 1 all over 3 factorial, which is 3 times 2 times 1. These will reduce, and the answer is 4. Let's pause, and you try the second two, and I will reveal the answer. And here's the answer. Okay, let's now take a look at what happens when order is not important. Suppose we match up some basketball teams, and we have basketball teams A, B, C, D, and E. They represent 5 teams. List all the possible matchups. So these are all the ways that these teams can meet together. I want you to notice that there are duplicates, because when A matches up with B, that's the same as B matching up with A. So all of the red strikes are the matchups. We don't really need them. So in the end, we only have 10 different matchups instead of the 20. Okay, well, this is called a combination. And the combination is a little different than the permutation in that there's going to be less of them because we are going to eliminate duplicates. The way we eliminate the duplicates is by taking the permutations and dividing it by the number of choices. So in this example, combination of 5 chosen 2, it'll be the permutation of 5 chosen 2 divided by the duplicates, which is 2 factorial. All right, so let's take a look at the next slide. All right, so here's the formula. If you don't want to remember it with permutations, you can just remember it this way. This part right here is the permutation part, and then divided by the number taken at a time. All right, so let's take a look at this problem, and we have a deck of cards, and we want to know how many different ways a 5-card hands can be possible. So the order is not important on the cards that you're holding in your hand, so this is a combination, and there are 52 cards, and we are going to choose 5 of them. So there we go. And so remember that this is a permutation of 52 chosen 5, all divided by 5 factorial. And that's what this is right here. This is the permutation part, which I just did in the numerator, divided by r. So this is going to be 52 factorial all over 52 minus 5 factorial, and then 5 factorial. Okay, and I'm going to rely that you can put this in your calculator and get it. Let's go to the next problem. Okay, let's practice doing these. So this is going to be 8 factorial all over 5 factorial, and I don't need that extra parentheses. Okay, 8 factorial all over 5 factorial times 3 factorial. So I'm going to do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. So all of these will reduce with all of these, and then I can see that 3 times 2 is 6, and I can reduce with this 6, and so the answer is 56. This one will be 10 factorial all over 4 factorial times 6 factorial. So this is going to be 10 times 9 times 8 times 7 times, and then I'm going to say 6 factorial. And then I know I have a 6 factorial here. So instead of writing them out, I know they're going to reduce. And then I have 4 factorial, which is 4 times 3 times 2 times 1. And I know that 8 will reduce with this 8, and one of these 3's will reduce with one in the 9. So this is going to be 30 times 7, and 30 times 7 is 210. I'm going to pause now for you to practice. So pause and see if you can get those other two. And here's the answer. Okay, let's pause and see if you can tell whether each situation is a permutation or a combination. Remember, permutations, order is important. Combinations, it is not. And here's the answer. Okay, your turn. Take a look at this problem and see if you can figure out the answer and what property we use. Pause. And here's the answer. Since order was not important, then we are just going to use a combination. Here's our last problem. Pause. And it is a permutations because putting the paintings on the wall, order is important.